but you will only going to get uh, yeah. So you are only going to get two values. Okay. Then in 1926, Erwin Schrödinger, he invented the wave function. Wave function is like a mathematical description, and it actually talks about, in simple words, it talks about the wave nature of the subject or the quantum object, whether that object is a electron or a neutron, or like a cavity in diamond or whatever. So whenever I say a quantum object or quantum mechanical system, I'm talking about something that displays the quantum properties. So I will use this word quantum mechanical system a lot in this lecture. So what Erwin Schrödinger invented is a wave function. He described the mathematical behavior of a particular quantum object. And later in the same year, 1926, Max Born proposed that, like, this wave function that Schrödinger has presented, it is actually a probability wave. And what it tells us is like, as we use F equal to ma in our classical mechanics, like if you are given that an object is at location x0 and a force is acting on that object, then you can calculate that after a time t where that object will be, whether it will be at x1, x2, or whatever position. Similarly, Schrodinger equation given an object, it can give us some good probabilities, some good uh, measures that where or like what that object will be doing. So, but again, we are only going to get the probability, and we are not going to get the exact results. Schrodinger equation is something that we use a lot in quantum computation. It is like behind the scene, but if you will look at the fundamentals, like then you would know that Schrodinger equation is used, even to reset a qubit, and then in many algorithms, this equation is used. So the next we have is the Heisenberg's principle, and this was proposed in 1927. There are many misconceptions around like this principle. It is called the principle uncertainty principle, and I would like to just describe it with one sentence, that it is prohibited to get the complete description of a quantum object. So that's all it tells us, that it is impossible to get, in other words, it is impossible to get the accurate measurement of all the properties, or we call like mutually exclusive properties of a quantum object or a quantum system. So let's say an electron is a quantum system, then you can never know the the values of spins along two axes simultaneously, or one example that sometimes confuses people is like the position and momentum. So it is being said, like, if you have to find the position of an electron, you have to hit it with a precise frequency photon, a photon with a high frequency, and then that photon is going to pass that energy to electron, and electron will displace. Then how you would know the momentum or the speed of electron? So that's a very good example to understand thing, but it sometimes it confuses people, like, okay, if I am going to hit, why should I hit? Maybe there is some other way to measure electrons position, and maybe I can also measure momentum same time. So it may introduce a, like, doubt that what uncertainty principle is. But what it is in nutshell is like, it is fundamentally restricted. It is restricted by nature, that you cannot get the complete description of a quantum object. And I have, like, written an article. I'll share the link in Discord, uh, with an like everyday life example, that what does it mean, and I'll also put a link to the article and a video later on. So it says, like, there's an equation that tells us like the uncertainty in the position and momentum. The uncertainty in position is delta x, and uncertainty in momentum is delta p, and it should always be greater than h bar by 2. So if you have a balloon, a square balloon, and if your measure of uncertainty is the width of the balloon, and measure of uncertainty is the in momentum is the height of balloon. So if you compress, you would like to get be more certain about the position, you will become, the balloon will expand, uh, vertically, and then you will have more uncertainty in the measure of momentum. In 1982, like we jumped to 1982, but a lot of things happened in between, so we cannot go through everything. But in 1982, the researchers from IBM, MIT, and famous Dr. Richard Feynman, they participated in an event, in a conference, and at the end of the conference, Dr. Feynman, he suggested that since we are trying to study, the quantum mechanical objects, we are trying to see why, like, if we are developing a drug, or if we are developing a new material, why things does not stick with each other, why we are not able to get new combinations, or which one is the stable combinations. So those type of problems, those are like the problems posed by nature. So, and those problems follow the laws of quantum mechanics. So, and what we are trying to do is trying to resolve those problems with help of classical computation. So that may not work. So he suggested to tackle the uh, problem. He actually um, use the problem as an opportunity. So instead of like looking at problem with the classical mechanics, he proposed that why don't we build the quantum computing devices where we can maybe manipulate a little and simulate things in on a computer, the simulate the things of quantum world on a computer. So this is how it started. So there are like some key concepts of quantum mechanics that we use in quantum computations, and three of them are very important to understand. One of them is superposition, other one is interference and entanglement. All three have their own importance. So when we say superposition, what it tells us that and we are talking about just one quantum object. So if we take one quantum object in account, that quantum object could remain in multiple states simultaneously. So we'll understand it with a like example of tennis ball. Let's say a tennis ball is our quantum system. It can be, but it is just an example. It's a very large object. So if we have a tennis ball, and the property of tennis ball could be its color, so red or blue, right? So when we don't look at that ball remains red also and blue also. So it remains in superposition. We do not have two balls. We just have one ball, but two properties. So, and that's all it could have. Like a bit could have a 0 and 1. So this tennis ball, when we don't look at it, it may remain in like red or blue, or a mixture of red or blue. And this is the same concept that we use in quantum computing. Like we use a quantum mechanical system like a ball that can remain in multiple states simultaneously, and we make it our fundamental unit of quantum information that we call qubit. So we'll know more about that. But there are two things. One is superposition, that quantum objects can remain and represent the multiple states at the same time. And other one is when you look at it, when you look at that ball, it could either be red or blue. When you look at it, it will not be red and blue both. And this is what is called the collapse of wave function. Or we say like, no, it is no more wave, it has become a particle. So particle will have definite properties, because we study particles with Newtonian mechanics. So the collapse of wave function is not the only theory that explain the behavior, that when you take a measurement, things comes in like one way or other. It turned out as one way or other. But there is another concept in quantum mechanics that is called the many world interpretation. It is like the concept used in science fiction movies also, that there is a multiverse. So what it says that when you look at the ball may be green in your universe, but it continue to exist in blue color in another universe. So this why I decided to include it in our talk is because it gives us a very good picture of quantum computation. So in quantum computation, we can think that computations is happening in multiverse. So if we have x equal to 1 2 3 and y equal to like 4 5 6, then if we put x in the superposition of 1 2 and 3 and y in superposition of maybe 4 5 6, and it's just a simple example. So there, one could also 8 2 3 4 separately, but let's keep it simple. So we can have this calculation happening with just one x variable and one y variable in multiple universe, right? So this is what we achieve the parallel computation with the help of superposition, where the calculations are happening in parallel worlds. Now interference we could understand best with the superposition of waves. When one wave, and I'm talking about the classical wave, so we can, with the classical wave we know like we have frequency, wavelength, and we also have phase, right? So what I mean by phase is, if you will see there's two waves here in the picture, the constructive interference picture here, then these are in phase. I call it in a phase because the peak is aligning with the peak. And when this two waves are superimposed on each other, I'm going to get a bigger amplitude of this wave. But if when a crest and turf of a wave, a peak and bottom of a wave, they fall on each other, we get nothing, and that's a destructive interference. So interference has the same meaning, but in quantum computing, the phase is very important. So uh, we interfere the same states. We do not interfere like one state with another, but we interfere the same state, and we see like we are going to get a better or a bigger amplitude for a state. If we get a bigger amplitude for a state, there are more chances to get that state as our final outcome. So interference, without interference and phase, we cannot take any advantage of parallel computation happening in multiverse, because we ultimately we are just going to get a probable output with the equal probability. So interference is very important. And third one is entanglement. Entanglement could have many definition, but the simplest definition is it's the correlation between two quantum objects. So you have to have more than one quantum objects, and uh, the way this correlation work is like, if you measure one of the quantum object, then you come to know about the information that you measured on first object. You come to know about the same information from another object, and that object could be far away, maybe other side of galaxy or somewhere. So spatial distance does not matter between them. Once the particle or entangled, they you know they remain entangled. So basically entanglement is being used a lot in field of quantum key distribution. That is a very hot field. And people sometimes, if you see videos, people talk about hype on quantum computation and all that. So it is not a hype, it is real, it is very much real. Governments are investing lot of money, especially in the area of national security. And quantum key distribution is very much real. The people in DRDO and defense are working on same. So that entanglement is a uh, you know must have resource for quantum key distribution or secure communication. And it is used a lot in almost all the quantum algorithms. And in many algorithms, when you will see um, later today or tomorrow, that we take measurement of a set of quantum objects. We perform a measurement on the set of a quantum objects, and those objects are linked or entangled with other objects. So when we take measurement on one, you come to know what could be the value on others, and that helps you a lot in quantum algorithms. So the quantum, without that uh, entanglement, you cannot get the exponential speed up. It is very much required when you compare the speed up with respect to classical computation. Entanglement is a resource that you need to gain the exponential speed up. So in short, we can define a quantum algorithms are designed to execute all possible computational path and cancel out the undesired outcome by destructively interfere, undesired solutions, undesired probabilities, and boost the probability of getting the right answer. So I think we have finished the first part. Freya, I'm sorry, I cannot look at the time. Do we have, how long we have?
Yeah, it's 10:54.
So we have half an hour, we could say.
Maybe yeah, like 15 to 20 minutes.
Okay, that's fine. So I'll move on without wasting any more time. Uh, so I would like to introduce the quantum bits. And quantum bits are the uh, fundamental building block of quantum information. It is analogous to bits. So bits could have only two values, 0 and 1. However, the quantum bits can have 0 or 1, or both 0 and 1. So we will, like, in fact, derive the equation that represent a qubit, and let's see how we do that. So whenever we talk about the quantum information and quantum object, we represent it states with this notation here, a bar, and as you see in the last row, the bar and a greater than sign, and it is called the Dirac's Cat notation. We did not mention about Paul Dirac, but he did a lot of stuff, of in after Erwin Schrödinger and Heisenberg. So Dirac invented this notation also. This is actually a column vector, and we as I said, like, the information is physical, so we can, like, get an object, quantum mechanical object, and we can make a qubit out of it. How would we mathematically represent that qubit? We know that you know uh, we represent it with psi, and we know it is some part of zero state and some part of one. So we if we have a spin system, we say, like, the up spin as 0 and down spin as 1. Or we have, like, some other system that could have two values, and since it's a quantum mechanical system, it can have two values simultaneously. So we can make the use of any physical system that displays the behavior, the quantum mechanical behavior, or the that can remain in superposition as qubit. So let's see if we can derive some mathematical formula. Now, what we could do, actually, we can use the same Dirac notation. It's a column vector, and we can, define, or sorry, not define. We can represent our quantum state as a vector. So we make use of vectors to represent our quantum state, and we see if that we are successful, right? If we could do that, because in order to perform calculation, we have to have some mathematical objects. So we'll see, like, if vector will be helpful, and we see, like, okay, we can get a projection of this vector in the state 0. We can get a projection of this vector on x and y axis. I named x axis as 0. And the way this circle, this is a unit circle with the radius 1. It intersect the state 0 at coordinates x equal to 1 and y equal to 0. So I have defined my column vector with the coordinates 1 and 0. I defined my, you know other, this intersect here, that I call the state 1. So the coordinates of this particular point is 0 1, x equal to 0, and the value of y is 1, because this is a unit circle. And I can very well, like, able to define this qubit with the help of vectors. What I could do, I can name this projection a0 and a1 on the x and y axis as amplitudes. So this amplitude, or I named this as a a0 and a1, and I am calling it amplitude. uh, Maybe, we can call anything at this moment. So, and one more thing is that, like, if I'm going to look at this qubit, I'm either going to get a 0 or 1, because due to the collapse of wave function. So the probability of getting one of this two state, either 0 or 1, is 1, right? So either I will get a 0 or 1. So in case, we can simply write it as a constant. So that constant tells us that the probability of finding 0 and 1 is should be 1. And why I used square is because we know, like, you know the quantum objects are like waves, right? And the energy of a wave is the square of its amplitude. Uh, that is one way to explain this. Another way is very simple. It is just a Pythagoras theorem. So if you will do a0 square and a1 square, like, you get the magnitude of this vector. So a0 square plus a1 square equal to 1 gives us a, like, a constant. So we can see, like, we can represent a qubit on the surface of this circle, but something is missing. What's missing is, here is, like, we know these states are wavy. So in order uh, to represent it properly, we have to have the representation of waves. So the waves include the phase, the waves include angles. So we have to refine our representation a bit, and for that we are going to use the complex numbers. So instead of using a0 and a1, we are going to use two complex numbers. The complex number is simple, like, simply represented as, like, the real part on x, and the imaginary part on y-axis. R is the magnitude of this complex number, and with complex number we also get the complex conjugate, and we can get the R with the help of complex conjugate and the complex number. So using, like, Euler's formula, and as I said, there's a lot of information here to digest, but you can actually look at this PPT later. So we can define a complex number with C equal to R E I theta, where theta is the angle from x-axis. It is also uh, what we call the phase. And with help of complex numbers, we are able to represent both magnitude or the amplitude, as well as the phase of that wave component that is associated with a state 0, and one that is associated with a state 1. All right. So again, in this case, we have to keep our constant, and our constant is c0 square plus c1 square has to be 1. In next screen, we will see, like, how we can derive Bloch sphere. That's an visual aid or visual representation of qubit. Uh, so coming, like, the mathematical representation, we have most general representation until now is psi equal to c0 0 plus c1 1. Now we can simply replace the c0 with r0 e to the power I theta 1, and similarly r1 e to the power I theta 1. And here I have done some, like, I have taken out I theta 1, the phase associated with the state 0. And then here I'm left with the phase difference. So that is all matters. We do not care about um, the global phase. What I mean by global phase, if, like, our 0 state and 1 state is apart by 45 degrees, and if you move both of them, um, you know we are not interested in knowing, like, if you move both of them together. But if you move, like, one with respect to other, that is what we are interested in, and we call it the local phase or the phase difference. So we finally come up with this equation, mathematical equation, psi equal to r0 0 plus r1 e to the power I phi, where phi is the phase difference. And then if we solve it further, we can see that we get an equation of unit sphere. So this unit sphere has, like, x, y, and z coordinates. Whenever we see this equation, we simply know that this is an equation of an uh, unit sphere that we also call, like, S2 sphere. And here we can, you know, further work on that, and uh, using some simple formulas, uh, in conversion between the polar coordinates and or the spherical coordinates and the Cartesian coordinates, we can derive that if we talk about uh, a sphere with radius r, the and we would like to represent the Cartesian coordinates of a point on this sphere. So here this point is making an angle theta with z axis, and the projection of this particular line, the projection that it makes with the xy plane is making an angle of phi with x-axis, with just like this two real angles, and the value of radius r, we can convert between the Cartesian coordinates and the spherical coordinates. So this conversion is written here. It is not very difficult to understand. Now, ultimately, what we get, if we, since the value of our radius is 1, r equal to 1, since we are talking about this constant is in place already, that x square plus y square plus z square equal to 1. So we come to, using the Euler's formula, we come to this particular equation that psi can be represented with help of cos theta 0 plus e to the power I phi sine theta 1, where theta is an angle that a particular vector, a point on the surface and the origin. So the vector that is starting from origin, and the tip of that vector is on the surface of this sphere. So that particular vector, the angle that it makes with axis z is theta, and the projection of this vector on xy plane. So this projection, the angle that this projection makes with the axis x, is called the phi. So using theta and phi, we can actually represent any point on the surface of this sphere. This all the states that we get on the surface of this sphere represent a valid qubit states, and we call it also call it the pure states. As you could also notice that I have marked, the state 0 upwards and 1 down, north pole and south pole. Similarly, I have mentioned the state, the intersect of x-axis with this unit circle as a state plus. So this point represent a state that is actually a superposition of 0 and 1 state, and then so I have marked it as a plus minus, plus I minus I. So now there could be a question, and I just wanted to make it clear that here on the Bloch sphere, the orthogonal states are opposite to each other. So when we looked at orthogonal states in this slide, we did see like the state 0 and 1 are at the 90 degree. They are making an angle of 90 degree. They are orthogonal to each other. But when we represent it on a Bloch sphere, those are like opposite to each other. It is because in the real calculation, what we do is we actually adjust this angle theta, and we make it theta by 2. What we do actually, we map all the points in the upper hemisphere, like the points which are from here to here. We take it and we map it on entire sphere. The reason is like we are not interested in global phase, and I have tried to explain it. If you have any question, I can further explain it in Discord. But what we are doing is we are trying to come up with an one-to-one mapping. So for each unique state of a qubit, I would like to have a unique point on this Bloch sphere. Otherwise, like what will happen if I'll use theta and this equation here, then what I'll be doing is I'm representing the same state at 2 points, two opposite points. But I do not want same state just differ by the global phase at two antipodal points. What I want is on the antipodal points, I want, sorry about that. So on antipodal points, what I want is, I want the orthogonal states. So the way I get it is, by making theta equal to theta by 2 and this mathematical equation, and you can play around that definitely. Moving to next slide, seeing the block sphere representation. This formula we have to remember. This is very generic formula. Psi equal to cos theta by 2 0 plus e to the power I phi sin theta by 2 for the state 1. Basically, again, as you can represent any arbitrary state, like here we have represented psi here. Uh, but what uh, the takeaway from this is like we are looking at two level quantum mechanical systems. So our system has 0 and 1, but we have many bases here. What I mean by basis is like if you have this state psi, you can either represent this state psi with the help of state 0 and 1 as a linear combination of state 0 and 1, or you can like represent it as a linear combination of minus I and plus I, or the plus state and minus state. So the definition of this plus state minus state plus I minus I is presented here, and you can do that calculation. But I have tried to explain it with the state 0. State 0 is the state where our unit sphere is intersecting with z axis. So this uh, same state 0 can be represented with the help of 0 and 1. So here the linear combination of 0 and 1 I have taken here at the bottom of the screen. So I'm multiplying 1 with a state 0, 0 with 1. And then similarly, I can represent the same state 0 with help of plus and minus and plus I and minus I. So these are like the basis states. So there could be n number of basis states. So it's not only limited with like 0, 1 or plus minus and plus I and minus I. Any arbitrary axis, any two antipodal points that you get on this sphere, you can cut the sphere in half, like you know like here, and anywhere else, and every time you cut the sphere you get a unique axis if it is passing through the origin. And you can take the values here and there at the two antipodal points as an orthogonal states, and you can express your arbitrary state, any state on this block sphere with the help of these 2 points. So there could be infinite number of bases possible, but in quantum computation we deal with only 0 and 1. Now there are like some simple single qubit operations I would like to talk about. And whenever we discuss the operations on in quantum computation, we talk about the rotations. So here in case of single qubit, we can rotate a state, and to rotate we need an axis and angle. That's all we need. And this is what you will read more about in the group theory in mathematics. All you need to rotate something is an axis. Around that you rotate, and an angle. So by what angle you would like to perform that rotations. So rotations are possible around any axis. But we have like some important matrices, important operations. Sorry, I jumped to matrix, but every operation, since we are talking about vectors are our states in quantum computing. So our operations are matrices. So we can use matrices, and there are three main Pauli matrices. Each matrices has like some formulation, and when you apply this matrices on a particular quantum state, what you do is like you rotate that quantum state around a particular axis. So if you apply sigma x, you rotate it around the x-axis, sigma y, you rotate around y-axis, and so on. So the rotations are always like anti-clockwise. So if you are at a state 0, you would like to rotate your state, this particular state, you would by 180 degrees around the x-axis. So this is your x-axis. This is where you are gonna follow. You will go through the minus state and you will come here. So this is what like 180-degree rotation, and this is a rotation around x-axis. Similarly, with the anti-clockwise you can do it again. So if you do it again, you gonna go to the state 0 again. So two poly x are equal to identity. Identity means you perform no operations. I have explained it with the matrix also. So and the poly X gate is also called the NOT gate. And as you could see here, I applied the X gate on the mathematical representation that we developed. And what it is doing, it is like, before the coefficient C0 was associated with state 0. After applying an X gate, the C0 now is associated with the state 1. So we have exchanged the probabilities, or basically probability amplitudes, but also the probabilities. And this is a simple circuit example, as you see here. And as a single qubit gate, we can rotate qubits not only around the xyz axis. We cannot, we can't only like rotate it by 180 degree, we can rotate it by any angle. So in order to get the operators associated to rotate a qubit around x axis, we use this formulation. And finally, this is how we put it on a state and get the final state. uh, Similarly, to x y z axis, we can have the rotation by any angle around any arbitrary axis. So that also is possible, and you can calculate the matrix based on the angle. Other important operation is an Hadamard operation. That is the very first thing that you do in any quantum algorithm. So what it does, like, it puts the state 0 in superposition of state 0 and 1. So you know you what you do actually, you again, for performing any rotation, any operation in quantum mechanics, you have to have an axis around that you perform the rotation, and an angle. So if you are at state 0, you take the axis xz, an angle it makes with a 45-degree angle it makes with x and z. You take this as an axis, and then you rotate by 180 degrees. So this is how you get a plus state if you are at 0, and then you go back to 0 if you perform this operation again. So again, that performing two Hadamard results in an identity, and it is all related with unitary matrices. So you can read more about that later. And then coming to application, I did heard Brian, and he was explaining all those applications. So basically, it is the same thing that at this moment we don't know what is the potential, but maybe in couple of years when IBM will launch a 1000 qubit computer, 1023 qubit computer, will be in better position to judge. And once that journey will start, we will have an impact that could be equal to bringing like fourth industrial revolution. uh, so we are going to see a major impact in almost every field. At least I'm confident of seeing that. So
Professor, Professor,
yeah, sure. And yeah, you can just call me Jayesh.
yeah, Jayesh, Jayesh, sir, can you try to wrap up in 2-3 minutes if possible?
Yes, I'm already done actually.
Okay, okay.
So I'm ready to face any questions and answer any questions if you have any. Okay, Freya, it's over to you. I think there are no questions. And if there will be any question, I do see something in chat. Is it about a question or something else? Can you check? Okay, so it's not a question. So I'm good with that. So Freya, we can actually conclude this sessions if there are no questions. And feel free, everyone, to post your questions in Discord.
Thank you so much, sir. Uh,
Yeah. Thank you. Thank you for having me here. Thanks a lot. Bye bye.
So we'll just